afternoon to you all wonderful and awesome matriculants. My name is Abram and we're in for a lovely show together. It's physical sciences and I know that you've got your thinking caps and we're about to learn more and learn extra together. But we do have our driver by the name of John. John, how are you?
I'm really well, thanks, Abram. Guys, greetings to you. Great to be with you again. Today we're looking at electrochemical cells. So I hope you're ready for it. Hope you're up to speed with it. I know your prelims are just around the corner, but you know what? This is the place to be to prepare for those prelims because we're here to learn more and to learn extra. Abram, how can they get the notes and enter competitions and do your thing? Let's hear about
guys,
that.
you need to go to facebook.com/learn extra, like our page, share the page with all your friends, your classmates. Remember, guys, it's not a secret anymore. You can tell everyone it is out there and people can get information through our page. Rather, on our website as well, learn.mindset.co.za. There's a schedule, there are notes, there are previous shows that you can watch, guys. So make sure that you go over the website. On Twitter, follow us at LearnExtra. We've got awesome giveaways for today's show. We've got the awesome Casio calculator. You win it by answering the test yourself questions. And remember, guys, it's just not about the calculator. It's also about testing yourself, challenging yourself, and getting to know what we are doing today. So, guys, do test yourself. The challenge question is also available, I believe, John?
It's just up now.
All right.
And, guys, it's an interesting one, so make sure you get a hold of it. We'll be looking at it in a minute. I just wanted to add something to what Abram said about the test yourself question. Up until now, we've been taking the winner with the highest score. What I think I'm going to do for this show, and perhaps for some of the other shows, is particularly for this show, I'd really like you to answer those test yourself questions. So I'm going to put the people, everyone that entered and submits complete answers, okay? You're going into a lucky draw to win the calculator. So you don't have to be the first, you don't have to get the most answers, but if you submit an answer, you could be in the draw to win the calculator. Isn't that cool?
That's so cool, John. You're being too generous.
No, but guys, I need you to answer. Okay.
Nice
so
one.
we'll make a lucky draw of it for this show particularly. Okay.
Awesome. Let's get on it.
Let's get on it. So, electrochemical cells, what are we going to do? Well, from grade 11, you should remember the whole story about redox. And we're going to revise what redox is. Reduction and oxidation reactions. We'll do something cool with that. And then we're going to look how that applies to some basic electrochemical cells. And there are two types of electrochemical cells, which we'll discuss in a minute. So let's have a look at the challenge question to start with. And here's an interesting word because it's not often used. Sacrificial anodes are used to protect other metals that oxidize easily. Which one of the following metals would protect iron metal from oxidation? Now, guys, this is particularly relevant. If you are living at the coast, you know that if you have anything that is iron, it rusts almost immediately. A little bit of salt water, a little bit of salt in the air, and you can leave a nice shiny piece of iron out overnight and it will more or less turn red in a few hours. You can watch it happening in front of you. So we don't want to have iron structures that just corrode and fall apart. Talking of which, Abram, you know what? When I was a student, I had an old Beetle. It was my mum's car, but it is so rusted that you won't believe it. On the corner of the door, we had to put a foot on the corner of the passenger door because it had rusted through.
Sure.
That's how rusted it was. So that was growing up in Durban and the coast. So you need to protect your vehicle.
Yeah.
Make sure you wash it. Even I washed it a little bit, but it wasn't enough to take away that rusting. Okay. So here's a really cool idea to ensure that things don't rust. Okay, so guys, there's science in everything that you look around, have a look and see what's happening to metals in your environment, and I'm sure that you'll see some oxidation, some rusting, some formation of oxides. And so what's that all about? Let's go to the first thing. And here we're going to do some quick revision about the direct transfer of electrons. And we're going to define oxidation and reduction. These are two important terms that you really have to know. And so you need to know that oxidation is a loss of electrons and reduction is a gain of electrons. And if you can't remember that, here's the way to remember it. Instead of learning that whole sentence, you just simply learn OIL, which stands for oxidation. Oxidation is a loss, so is a loss. And then you remember that going with OIL is the word RIG. And reduction is a gain. So oil rig makes it very clear. There's another term that you need to know, and I'm going to demonstrate this with Abram. So Abram, get yourself over here just for a second.
Yep.
We have something called an oxidizing agent and a reducing agent. Now, I want you to look at Abram. He's over here next to me, and he's a really rad guy. He's so cool, he's a secret chemical agent. So that's the game that we're going to play. Now, with secret chemical agents, maybe I'll be the rad one. I don't know who's more rad, hey?
It's you, John. Take it.
Am I the rad?
Yeah, you are.
And you're not?
In your times.
Okay, in my time. Okay, so if you want to be really rad, okay, is rad a word that we use?
Yeah,
it's a phrase.
Yeah, it is.
Okay, so rad stands for this. A reducing agent donates.
Wow, John.
Okay? A reducing agent donates. You got it. R-A-D. Reducing agent donates. But now watch what happened there. The reducing agent donated. Okay? So what happened to Abram? He gained, imagine that this represented electrons. So the reducing agent donated. What happened to me? I lost electrons because I donated. In losing, I donated. Losing and donating is the same thing. So what happened to me? I was the reducing agent. I underwent oxidation. What happened to Abram? He gained the card. He gained the little gold card. Okay? So he gained it. He had to take it. I could have held this over here like this and said, Abram, I'm donating it to you. I'm donating it to you. I'm giving it to you. And until he opens his hand and he takes it, he's not going to get it. So you need two agents for this redox reaction to take place. You need an oxidation and a reduction reaction. You need a reducing agent and an oxidizing agent. So now let's think about it. Oxidizing agent does what? What did you do?
I received.
Yeah, but don't say R. What did you do? I mentioned it with the T. You took.
I took.
So an
from
oxidizing agent takes. Reducing agent donates. Okay, so don't get them mixed up. Reducing agent, rad, cool. Oxidizing agent, OAT, O-A-T. So that's how you remember it. These mnemonics are helpful to remember important concepts. You got it?
I got it.
So what happened to you? You took
And I gained.
and you gained electrons.
Yes.
So you underwent what? What process? Reduction or oxidation? Look at the board.
Oxidation.
Reduction is a gain. Oxidation is a loss. So what did you undergo?
R-I-G.
You went reduction.
Yes.
Okay.
Yes.
And you were the oxidizing agent,
Agent.
because you took
Took,
electrons. You made oxidation happen. Who got oxidized? I got oxidized. Who got reduced? You got reduced. Who made you get reduced? I made you get reduced. You get it?
I get it.
So I'm the reducing agent. You're the oxidizing agent. I underwent oxidation. You underwent reduction. Cool. Guys, I hope you've got that. Hope you can see the coupling. Act it out for yourself. Get somebody to exchange stuff with you so you can see. When there's a loss, it's oxidation. The thing that is making the loss happen is the thing that's taking it. It's the oxidizing agent. Work it out for yourself. I hope you've got it. And I'll take this back again.
Okay.
Thank you. Okay, guys. So that's the definition of oxidation and reduction, oxidizing and reducing agents. You've got to know that. And you've got to be able to apply it. We'll sort it out in a minute. Let's do an example so that you can see what's happening. And we'll put some arrows in here as well. So we've got an example here of, first of all, let's just choose this little arrow. and I want it like that. I want that one there, and we're going to put an arrow over there like that. We're saying that zinc plus copper sulfate goes to zinc sulfate plus copper. Now, look what's happened. They've just swapped partners. There was zinc, and it was on its own, and copper had a partner. Copper ions were in partnership with sulfate ions, and what's happened is that the zinc has come along and it's taken the copper's place and it's kicked the copper out, and copper has landed up on its own, and we've got the zinc sulfate there. And in that process of exchange, what I want you to see is that we can show what's happened to the ions. We can exclude the sulfate ion because the sulfate ion is just a spectator. Nothing happens to it. But look what's happened to the zinc. The zinc started as a metal. It ends up as a zinc ion. What's happened to it? Zinc went to form zinc 2 plus, and in addition, plus 2 electrons. So what did it do? It lost those electrons. Where did those electrons go to? Well, it started with copper, and copper along the way picked up those electrons and ended up as a copper metal. So what happened to copper? Copper 2 plus gained 2 electrons to become copper as the metal. And so we write these as two separate half reactions, and we've identified them. This one, notice, is where there's been a loss of electrons. Why, if it says plus on this side, are we saying loss? Well, if it was plus on this side, it would have to be a negative on that side. But we don't write it as negative. We always write it as positive. So that's why that's the loss of electrons. Whereas here you can see clearly copper 2 plus has gained electrons to form copper. And the overall net equation is exactly the same as the one that we had just now, except it's just showing the ions. Okay, so there is the transfer of electrons. Zinc has donated electrons to copper. Copper has accepted them, has taken them, and we've got a transfer. Wherever you've got a transfer of electrons, that is known as a redox reaction. You can assign oxidation numbers, which we will carry on with next week, to show where this sort of reaction has happened. And you might have done oxidation numbers in grade 11. We'll just revise it next time when we look at applications of redox. Now, one of the ways of this electron transfer happening is in an electrochemical cell. When we separate, instead of that all happening in one container, we can separate the reactions into two different containers or two different half cells. And then it allows us to have a stream of electrons moving between them and a stream of ions moving between them. So now there are two types of cells, and we're going to look at the first one. We're going to look at an example of a zinc-copper cell. It's known as a galvanic cell. Okay? And this galvanic cell, it takes chemical reactions and it produces for us a transfer of electrons, a flow of charge. So it's like a normal battery that we use. It's very similar, but in this case, it's a wet cell. It is all in solution. So let's have a look at the reactions that are happening. And what I'm going to do is I'm going to add to it as we go along. So because some of this writing is a little small, I'm going to say on this side, I've got a copper plate over there. And on this side, I've got in a different color, I'm going to write a zinc plate. So there is zinc at that plate. And what I need you to see, you've got a beaker over here, and we've got the copper plate, which I'm going to draw in orange because copper is usually an orange color. I think you can see the gray. Connecting between them is a voltmeter over here, and we're just going to put the voltmeter in over there. Very important, in between those two solutions, we've got what we know as a salt bridge. It connects the two half cells together, and it's known as a salt bridge. Now, in this half cell over here, we've got a solution. In this half cell, we've got a solution, and this one will be blue, and this one is a colorless sort of color. It doesn't have a particular color. So now the reaction that takes place when we do this, when we connect the two together like this, is the zinc undergoes exactly the same reaction. Zinc prefers to be as an ion. So we get zinc going to 2 plus 2 electrons. So I want you to imagine now, we're going to talk about a little story. Imagine that you're a zinc atom and you're sitting on the side of a swimming pool. Here you are on the side of the little swimming pool. And you'd really like to go for a swim, but you've got shoes on. And you've got 2 pairs of shoes, and you know that you're not allowed to swim with shoes on. So here's the silly story that the zinc atom jumps into the water and becomes a zinc ion. Okay? It's a silly little story. But it leaves behind its 2 electrons on the plate. Where are these electrons going to go to? The electrons move through the wire towards the other side, towards the copper. And now suddenly we've got an extra 2 electrons, which we kind of think about as their little shoes, sitting over here. And here we've got a copper ion sitting in the solution. Let's just draw that a little bit clearer so you can see it. I'm going to take away the blue color. Copper solutions are blue in color. But there's the copper 2 plus. And the copper 2 plus doesn't want to get out of the water. But you know what? There's this attraction for these electrons. And it's hard to resist. So the copper jumps out of the water. And it jumps up onto the plate. And it changes color. It becomes orange. Okay? So this whole plate becomes a bit bigger. And what we find is that you've got copper 2 plus gains 2 electrons to become copper metal. And that's it. There's been a transfer of electrons. Now, guys, there's been a movement of electrons through the external circuit. And this only happens when there's a chemical push between them. The reason it happens is that zinc is a more reactive metal than copper. And it forces it to happen. But it wouldn't happen unless we completed the circuit. And so what you need to understand is that at the same time as this is happening, negative ions are moving through the circuit to complete the circuit, and that makes the salt bridge. Now, we haven't got too much more time to deal with this. I just want to do 2 more things. Very, very important. On the electrochemical cell, we've got to identify the names of the electrodes. The names of the electrodes are given according to what type of reaction is happening. So where there is oxidation, a loss of electrons, this is the reaction that we see here, a loss of electrons. This is called the anode. Okay? And oxidation takes place at the anode. Oxidation. Notice, here's another trick to remember. The A and the O go together. A and O, they are vowels. A, E, I, O, U. A and O are vowels. But here's another cool thing. This electrode here, it's called the cathode. And it's where reduction has taken place. Reduction. Gain of electrons. The way I remember that is I always look for the red cat. Reduction, cathode. Oxidation, anode. Guys, it happens for all electrochemical cells. We've just looked at one. We've looked at the galvanic cell, the one that takes chemical energy and produces electricity. The other type of electrochemical cell is known as an electrolytic cell. And that's used for electrolysis, for refining metals, for recovering ores. We'll do a little bit more on that next week. But the same principle applies. Anode, oxidation, reduction, cathode. Learn it. Make sure you don't forget it. Okay, Abram, I think we've done enough for the moment.
Yes, I think we have. But the Mindsetters also have the challenge question during this break. So guys, get on it. And even the test yourself questions, because there are prizes up for grabs for you guys. But that's not the intention. But you must learn. But we'll see you after this break. Welcome back, Mindsetters. Now we've got this awesome competition. You know, we always have some giveaways. It is Get Connected hashtag with prizes, proudly sponsored by Vodacom. We've got airtime vouchers for you guys, 55 rand airtime vouchers, and we also have 3 Sony Xperia L cell phones. One has been won already, so we've got 3 up for grabs for you guys. All you need to do is to check the pinned post on top of our Facebook page. It has got instructions that will tell you that you need to register on Curio using the code LEARN, LEARN, upper or lowercase, it doesn't matter. Register like your teacher, and then go vote for your teacher on Facebook by liking the picture of your teacher. It's as simple as like that. But for airtime, you need to share that post, guys. It's pinned on top, so get sharing. The more you share, the better your chances.
Absolutely. Guys, please get your friends to register and get connected. Remember, we're here for you until you write your final exams. The only way you can get maximum benefit is if you stay connected. So don't miss a thing. Stay with us for all the activities coming up. There's spring school, there's exam school, there's a whole lot of revision taking place. We want to help you get the best marks you can. Okay, so let's get on to the questions now. We didn't summarize everything, but I need to remind you that everything is on the notes. So go and have a look on the notes. Okay, question number 1. It takes us from a prelim paper written in Gauteng in last year, and it gives us this picture. I just want to make the things a little bit bigger. We're told that we've got chlorine gas over here, going in over there, and in this solution we've got sodium chloride. That's an aqueous solution. There's a salt bridge, and over here this is a tin electrode. SN is tin. Even if you didn't know it was tin, doesn't matter. This is SnCl2 aqueous. Okay, we know that there's a salt bridge. There's the voltmeter, and the salt bridge connects the two in half reactions. Now, there is a line over here which I just want to highlight and make it a little bit clearer. This line, and I don't want the arrows on it, so I'm just going to remove the arrows. I'm going to make it like that. That line is said as an electrode A, so that you can see this is electrode A. Right. Now, when you're given something like this, you've got a salt bridge in place. One side has got gas bubbling through it. The other side is a solution with a metal inside it. You know that this is a galvanic cell. It's just like the one that we did in our example. It's like the zinc-copper cell. And so we know it's a galvanic cell, and we're asked to write down what is the energy conversion that takes place in the cell. Galvanic cell, we've got chemical potential energy. So chemical potential energy, and it gives out potential, it creates electrical potential. And so that electrical potential can be used to drive a current, and that's why we've got, in a closed circuit, we can get potential energy. So from chemicals, we get electricity. What's the other way around? Well, that wouldn't be a galvanic cell, that would be an electrolytic cell, where we use electrical potential to force a chemical reaction to take place. This is the natural occurrence. It happens spontaneously. When we put reactions together, some things are more reactive than others. You get some strong reducing agents and some that are weaker oxidizing agents. You put them together and they will react spontaneously. You don't need to add any energy. That happens in a galvanic cell. Okay, let's move on. Now, the next thing, we're dealing with these gas electrodes. And it says to us, name a suitable material that can be used as electrode A. Now, if I look at electrode A, I'm seeing that the gas that is bubbled in is chlorine gas. Now, what do I know about chlorine gas is that it's highly corrosive. So I don't want to have another reaction happening there. I want something that is more neutral. And the most common electrode for a gas electrode is the platinum electrode. So I would go for platinum. It is expensive, but in industry it's used quite often. An alternative would be graphite. And graphite isn't going to be corroded much by chlorine. So the next question, let's move on. It says, is electrode A positive or negative when the cell is working? Now guys, this takes us to the nub of the question. This is the really important part. We've got to decide what the things are in the two half cells and what they're doing. So at the moment I haven't even begun to answer it, but I'm going to start working out the reactions that are taking place. And fortunately for me and for you, on the data sheet, in your matric exam paper question, you will always be given two tables of standard electrode potentials. This ranks the reactivity of the different substances in order from high reactive, good oxidizing agents, good reducing agents, and it puts them in order. Now, there are two tables. I'm going to use table 4B, and I'll show you exactly what that is. You might have been shown 4A in your textbook or in your class, but I like to use 4B. And the reason is, it doesn't really matter which one you use, but I'll give you a reason why I like this one. If we look at this, and there's some writing that I haven't included on the side, it tells us that these at the top here are on the right-hand side. And on the right, we've got reducing agents. Okay. And the ones that are at the top are the strongest. So that's how I remember. The strongest, where I've got lithium at the top, it's on the right of the arrows, and it's the strongest reducing agent. At the bottom on the left, you can always find it. The bottom on the left, you've got fluorine. Wherever you are, you must know that that fluorine is the strongest oxidizing agent. Oxidizing agent. So you need to work with that. If it's the other way around, fluorine's at the top, they give you the table with fluorine at the top, then you're going to have to work with it. But normally you've got a choice. Now there's something I want you to see about this. Notice that the strong oxidizing agents have a big positive value of E0 or E cell, and the ones that are strong reducing agents have a negative value. So the strongest reducing agents, the bigger the negative value. And that kind of makes sense. The more negative something is, the more able it is to donate electrons. The more positive it is, the more willing it is to donate electrons, negative. When it's positive, it wants to take electrons to become neutral. Now, on this table, although it's very long and you can't see the whole thing in one go, in the middle, over here, we've got the hydrogen standard electrode. And it's noticed that that is 0, a value of 0,00 volts. And we use this measure to compare everything else against it. So we need to have two things that react. We want something that's going to take the part of a reducing agent and something that's going to take part of an oxidizing agent. Now, in our reaction, what did we have? Let's go back to the question, and you'll see that on the half cell, we had chlorine gas, and it became a chloride ion. So we're going from chlorine to chloride. That's my little interpretation of it. Plus 2 electrons. And on this side, I've got zinc, sorry, not zinc, but tin, and I'm going to do it in a different color. I'm going to say tin has gone to tin 2 plus 2 electrons. I don't know which one of those goes, because remember, these are reversible reactions and it could be either way. We don't know the competition yet. Let's go and check on the table. So we've identified that we've got tin chloride here. Does chloride have anything to do here? No, because there's no chloride there. So it was definitely the tin that was reacting to produce the tin in solution. It could have gone that way or that way. We're not sure. The chlorine could be making chlorine gas, or it could be making chlorine ions. We don't know. But let's go and compare now on our table. So let's see, what's the relative position of tin and chlorine? So the way I do it is I start at the top and I move down from the right. And I'm looking for SN, my tin. And there I found it. You see, it's the first time I see SN, and that is your equation. So we know that that's the reducing agent. Notice we haven't seen, if I move my finger down, any sign of either chloride or chlorine. There's nothing, no chloride, no chlorine. The first one that I've come to from the top is tin. And it has a number associated with it of minus 0,14. Now, if I carry on down on the right-hand side, I will eventually get to chlorine down here. But what I want you to do is rather in your head follow this rule. We're going to write that equation down. Then we're going to go down on this side. We're now looking for the oxidizing agent. And we go all the way down until we find, there we've got it, chlorine. And can you see the shape now that I've made? Hopefully you can. The blue line went down like that in an anti-clockwise direction, and it's made the shape of a C. Okay, we had our tin over there, and our chlorine over there, and our chloride has been formed over there, and our tin 2+ is formed over there. So we must bear that in mind. So we now know that tin is the reducing agent. It's where oxidation is going to take place. That is the anode. This is where we are gaining electrons. It's the oxidizing agent, and it's going to be a reduction reaction, so it's the cathode. See, all this little piece of these bits of information are going to help us answer the question. You need to be thinking it through and making sure that we answer. Right, let's go and see what happens. Go back to our question and see if we can answer it now. What was the question? The question said, is electrode A positive or negative when the cell is working? Well, we've just established that we're going to take the chlorine and it's going to gain 2 electrons and it's going to form chloride ions. That was from our half reaction sheet. We saw it in that C picture. The chlorine gas gains 2 electrons to form chloride ions. So now if it's gaining electrons, guys, here's the trick that I need you to understand. If it's gaining electrons, what are electrons attracted to? Electrons are attracted to something that's positive. So this must be the A must be positive. Must be the positive electrode. Why do I say that? Well, you see, at the other electrode, let's just argue it through. What's happened is the tin has donated electrons. Electrons have moved from here. Electrons are moving to there. So where electrons move from is the negative electrode. This must be the positive electrode. Electrons are attracted to the positive. The source of electrons are going to be negative. So that's why this is negative, this electrode is negative, and that electrode is positive. Got it. Let's move on, because I think we've got most of the things sorted out now. Next question says, write down the formula of an ionic compound that can be used in the salt bridge. Now, the salt bridge needs to allow for movement of ions. As much as electrons moved in the negative in that direction from the anode to the cathode, And you need to understand that. The salt bridge helps negative ions move from the cathode back to the anode. And so we need something that's not going to clog up, that's not going to precipitate. We need something that's highly soluble. And the preferred substance is potassium nitrate. Now, notice it said write down the formula. So I can't write down in words potassium nitrate. I must write down the formula KNO3. Okay, next part of the question, go to another slide, and hopefully we'll sort things out. In which direction will electrons flow in the external circuit? Well, we've answered it already. We've already established that the tin is the anode, so it's going to form, it's going to undergo oxidation at the anode, so it's going to be from the tin, sorry, we must write down from the electrode A to there, or from tin to electrode A. I'm going to choose the second one. From tin to electrode A. Now, we've got the next question, which I absolutely love. This is an amazing question, and I really want you to get it because it's so important for us to understand. It says, in which direction will each of the following ions present in the salt bridge flow? Only write down towards the tin. SN is tin, ZN is zinc. Tin half cell, or towards the chlorine half cell. So now, what are anions? Anions are negatively charged ions. Negative ions. Now, what are the negative ions that we've got in the solution? Well, remember in the salt bridge, we would have the nitrate ions and we would have chloride ions. Those are the negative ones. So over here, look what's happening. Let's just write this out so we've got it. Chlorine goes to form chloride ions, 2 of them, plus it gains electrons. Okay? The chlorine's gained its electrons. Is that right? Sorry, I've got it wrong. I've written it incorrectly. It must be on the other side. Chlorine gains 2 electrons to form chloride ions. That's right. So the chloride ions, we've got more of them here. Now, initially when we started, we had the same number of sodium ions and chloride ions. Now the cell's going to quickly give up working if there's not a path for that extra chloride ion to move across. Fortunately, there was the same number of zinc ions and chloride ions in this solution. They were the same number. Even though the charges are not the same, for every one of these, there were 2 of those. Now, if we take one of these away, if we take one of if we take one of the zinc, the tin ions away, we take one of those away, what are we going to need? What are we going to need? We're going to need, let's just take that away for a minute, we're going to need a partner. We're going to need a partner for these. So where's that partner going to come from? Remember, we've got extra ones of those there at the moment because we are taking the chlorine gas is forming chloride ions, and here we've got a problem. We're wanting to have some more positives here. So what's going to happen? We're going to have let's just see whether I've got this. I really think that I might have been doing something wrong here. No, I've got it right. I've got it absolutely right. And what we're saying is, I didn't write this equation down. Tin goes to form tin 2 plus 2 electrons. Remember, the electrons are going that way, so it's not going on to there. It's making some extra ones. So I had it right the first time. The chloride ions are going to come along, and we're going to get 2 chloride ions for every extra one that we've got into the solution. So the anions are going to move which way? Towards the tin half cell. Now, what about the cations? Guys, here we've got a problem. Let's see what the problem is. Where's the imbalance? We had too many chloride ions there. Remember, we had too many chloride ions there because all the time we were making chloride ions. And so we had too many. We had to give them up. We've got too many here. So we haven't got enough of them here. So we've got to have to move them across so that we can get more partners in. Now let's look at the cations. Here, we started off with an equal number of those and those. Equal number. Positives are all fine. Here we've got an equal number, positives and negatives there like that. So now, what's going to happen? I'm going to get more chloride ions. More chloride ions because of this reaction up here. Go back to it. This reaction is giving me more chloride ions. So I've got an extra chloride ion. If I've got an extra chloride ion, how am I going to neutralize it? Well, I can't use the tin because the tin ions, I can use the tin. What's happening to the tin? I'm making more tin ions, but tin is big and heavy. I'm making tin ions and I'm making extra of these, but they're big and heavy. There are smaller ions that could possibly move across there. And those would be in the salt bridge, your potassium ions, and maybe some of your tin ions. And in that way, we would move them towards the chloride side. So your ions here would be your tin ions and your potassium ions. And which way are they going to move? They're going to move towards the chlorine half cell. Sure, I know that was tough, and I know we've gone on for a little bit, but I hope you've got it because it's the most important part of this type of question. So, Eddie, let's go for a break.
Thank you, John. After the break, we've got the challenge question and the winner for the Casio calculator. Stay tuned. Welcome back, my sisters. Now, the moment that we've all been waiting for, crossing our fingers, and the winner for the Casio calculator is Mawande Sivela. Congratulations to you, Mawande Sivela. This awesome Casio calculator is coming your way. So get entering, guys. More details are on the page. John, back to you.
Thank you so much, Abby. Now, guys, I know that last section was quite long. We still haven't finished the question, but although we've answered most of them, I just want to go through them quickly, because by looking at the half reactions, we've done it. So I'm going to fill them in as we go. Where did oxidation take place? We know that oxidation took place when zinc went to zinc 2 plus 2 electrons. And we know that the reduction was the chlorine gas gained 2 electrons to form 2 chloride ions. And remember, we did that right at the beginning, looking at the half reaction. So the next thing we're going to do is we're going to add these two together to get the net reaction. We're going to say zinc plus chlorine. Now notice when you add them together, one underneath each other, the plus 2 electrons and the plus 2 electrons cancel out. And we're saying the overall reaction then is zinc 2 plus 2 Cl minus. The last part, well, not the last part of this question, the second to last part of this question is to calculate the initial EMF of the cell. And the EMF of the cell is given as the E cell is equal to the E of the cathode. I hope I get it right, minus E naught of the anode. So let's check it, and we'll know that if it's wrong or right, because we know that it needs to be a positive answer. So if we go to the anode value, which was minus 0,14, and we go to this value, which was the cathode, so it's cathode minus anode, 1,36. 1,36 minus 0,14, and check it on your data sheet. You'll see that I'm right. 1,36 plus minus minus because of plus, 1 comma 4, and the answer for this is 1 comma 5. So this gives us 1 comma 5 volts. So that's the E naught of that cell, and then write it down in cell notation. Guys, you've got to learn this. This is a standard cell, and cell notation is one of those things that you need to remember. We start with the anode, so we're going to say we started with the electrode, which was a tin electrode. It went to SN2 plus, aqueous. Now, because it's a standard, we should also include that it's 1 mole per decimeter cubed. And then we put 2 lines. That represents the salt bridge. Then next thing we come to is the platinum electrode. And so we're going to write platinum as the next thing. And then we're going to put 2 dots. And we're going to say, what has happened? We've got chlorine gas. Okay, chlorine gas goes to form chloride ions. And we put that like that, aqueous. And you should really, if we're being pedantic, put 1 mole per decimeter cubed. And in fact, if we got the hydrogen, it's a gas cell, they can also ask you to put what the standard conditions are. The standard conditions are a temperature, get this, of 25 degrees Celsius. You can convert that to Kelvin, which is 298 Kelvin. And at the same time, the pressure needs to be 1 atmosphere or 1,013 kilopascals. So those are all questions that you can relate to that. Make sure that you've got those sorted out. Now, I think the next thing that we're going to do is we're going to look at the challenge question. Have we got any answers for the challenge question?
Yes, John, so many answers.
Let's see.
They are right answers.
Tell me, what's the most popular?
Okay, most popular should be the first, the Mg.
Okay, so is it which one
Mg.
of the following metals would protect the metal from...
B.
So what's the most popular? B.
Yes.
Has anybody explained why B is the most popular?
Yeah, there are some that explain.
Okay, so give us an explanation. Give them a shout out as well.
Nivo Mamatuba says, excuse me, magnetism is the highest reduction agent.
Magnetism? Magnesium.
Magnesium, sorry.
Okay.
Magnesium is the highest reduction agent. It has the ability to readily lose electrons.
Okay, excellent. Now, let's try and explain that whole thing. First of all, I'm going to go and look at my table of half reactions again. So, guys, we had to compare, in this case, iron and some of these others. Okay? And what Matuba, is it, what's
Mamatuba.
Mamatuba is saying is that if we're looking at iron and we're wanting to protect iron, look what iron will normally do. Iron will normally lose electrons. Now, the only thing that can prevent iron from doing that, it's going to react with oxygen, okay, mostly. It could also react with some of these other gases there, but it's likely that it's going to be that one, or it's going to be the oxygen lower down. Might not even be on this table of half reactions. But there's an oxygen down there to give us water as well. And I don't even think that there's the correct oxygen is on this table. But basically, we want to stop iron going that way. So in other words, what are we going to do? We want to stop iron undergoing that. We must choose something that is more reactive than iron. Then iron just becomes a spectator. So iron doesn't get reacted, but the other substance, one of those other substances, becomes the sacrificial anode. And what we mean by that is we're sacrificing that thing, and it becomes mess so that iron remains intact. Okay? So of all the things that we were given in our question, you'll notice we had mercury, silver, copper, and magnesium. And the only one that is on the table that is above iron is magnesium. There it is. It has a more negative E naught value. Because it's more negative, it will react more easily with chlorine or with oxygen or with any of the strong oxidizing agents. And what will iron do? It'll just sit there and it doesn't do anything because all the attention is focused on the sacrificial anode. Okay, so it was kind of like in the old days. I don't know if you know this, but in the old days when people were lined up to do battle, what sometimes the clever statisticians would do. So you've got a strong army coming to surround your household, your compound. And so what you do is you send a little force, a small force of very brave young men, or maybe even some 1 or 2 young men and a lot of the older, weaker men. And you sacrifice them. You make them run off in one direction. And if they run off in one direction, perhaps the army that was camping against you would chase them. And then your real troops would come and ambush at the back. Okay, so that's the idea here. You're sacrificing the magnesium to protect the iron. Got it? Mm. The reason we use a more reactive substance as the thing that is going to be sacrificed is that it will react more easily. Okay, excellent. Are there any questions on the page?
Yes, there are, John, especially on 1.6.
Okay, let's go back to 1.6 so we can get it. 1.6.
Papa,
our story of anodes, anions, and cations. Right, let's go.
Right, Papa Lo and Ste says, why are the ions moving through the salt bridge towards the SN half cell?
Okay, let's play this game. I want some blank paper. I want some blank sheet. So let's understand, first of all, that when you start your reaction, and I'm not even going to use the tin. This applies for any galvanic cell, okay? It applies for any galvanic cell. What you've got to recognize is that to start with, for every one of those, for every positive, you've got a negative. And for every positive on this side, I want to use a different color, A, you've got a B. They're equally matched, guys. Same number, okay? When we connect them, what you've got to recognize is that you create an imbalance. So if this thing goes up there, you've created an imbalance. The ions move through the solution to restore the imbalance. And unfortunately, that's the only time that I've got.
Thank you so much, John. It's been an awesome show.
Great. Guys, all the best to you.
Right, guys, remember, you can always get our notes and our videos on learn.mindset.co.za, but it doesn't end there. We have past exam papers that could be useful for you guys, and all the best as you're studying. Know that we always believe in you guys. So from me and the rest of the team, we just want to say, peace.